So I'm going to start figuring out what's going on in this electrolytic cell. I'm going to end up drawing it even though it's not one of the questions. So I need to figure out what's the strongest OA and the strongest RA. The strongest oxidizing agent always occurs at the cathode. Doesn't matter what type of cell. Okay? The strongest reducing agent is always going to react at the anode. In that potassium iodide lab from the previous class, you got that nice visual of the chemistry occurs right at the electrode. The bubbling in the potassium iodide lab was right against the electrode. The brown was coming right out of one of the electrodes. So lead is a neutral metal. I'm not even going to look at my table. That's an RA. All metal ions are OAs. Sulfate, I'm going to have to look that up. Sulfate comes in some pairs. So that's going to take some time. And I know water can be an OA or an RA. So look in your table, find some of those sulfates and see if we have any of the pairings here. Sulfate, even as a teacher, is the hardest one to do quickly. I just know to look carefully and not rush. As I'm scanning through, I'm not really seeing sulfate on the OA side of my table. But on the RA side, I do see lead and sulfate, middle-ish. Solid lead and sulfate ions are a decent reducing agent. If you then start figuring out what's your best OA and your best RA, OA, we've only got two, zinc and water. They're both pretty bad, and they're right next to each other. The zinc 2+ is one above the water, so it's slightly better. So the strongest oxidizing agent by a tad is our zinc ion. Now this question asked me about the cell potential, so I'm going to make a note of that cell potential at the end of my equation. Negative 0.76 volts. That is the reduction potential of the half cell. My strongest reducing agent that's going to react at the anode, I've got to look at water and sulfate and lead. And if I start at the bottom and see which one I hit first, I hit the lead and sulfate first. I hit that before I get to the lead and way before I get to the water. So the lowest one down was this pairing. Solid lead plus SO4 2-. And that cell potential is minus 0.36 volts. When you figure out the E0 cell, we'll maybe write this underneath and we'll have our first answer. Minus 0.76 volts. Subtract, so I'll do that in a different color, minus 0.36 volts. You end up with still getting a negative number, negative 0.40 volts. So this is in fact an electrolytic cell. It's not something like corrosion that can happen all on its own that we talked about before. It's non-spontaneous. So this is telling us we're going to need a battery or a power supply to run this cell. How big a battery? How big a power supply? Well, it's got to be at least 0.4 volts. Okay. What is the minimum voltage? Well, the bare minimum we need to put in is the positive version of our cell potential. Okay. Watch for this on tests or quizzes. If I ask you for the cell potential, you do it as we've done before. It's negative. What is the minimum voltage? It's the positive version. So you really need slightly more, but the way the test questions are worded, the bare minimum is this. Okay, you'd always use a little bit more, okay? But this would set the minimum. You're right that if you put this in, you're going to get 0. It's not really going to run at the minimum. You really need slightly more than the minimum. Asking you for slightly more makes a hard question to mark, and it's not how the diploma would do it if somebody wrote it. Okay, that asks you for the minimum, it's just a positive version of the cell potential is what they'd want, and that's what I'm going to want if this is on the test. So that's the one new bit. I've answered the 2 questions in this slide, but I just want to draw this cell and before you start practicing. Okay. Particularly with throwing that battery part in and figuring out what chemistry is going to occur. We got 1 beaker in an electrolytic cell, like you would 1 Petri dish in the lab. I'm going to put my 2 electrodes in, making sure I have room for my external cell at the top. Both of these are lead. My solution has zinc 2+ ions and sulfate ion. I didn't write the aqueous just to try to keep my diagram a little cleaner. I need an external cell. If I ask you to draw this, you must include a power supply. It's non-spontaneous, so you need a battery. I'm putting PS for power supply. And let's label a little bit of the chemistry. Okay, I may ask you questions on a test like which electrode gets heavier or lighter, or does an electrode stay the same mass? Now our 2 products at the cathode, we're going to make solid zinc, and that's going to happen right on top of the electrode. It would get heavier. At the anode, we're making a solid, I forgot to put in the S, but it's ionic. It's not a metal, and that's just going to fall down to the bottom. Okay? Only when you make a pure metal will it stick to the electrode. Okay? So which side is going to get heavier? Which side's the cathode? Is the left the cathode, or is the right the cathode? And I am being a little mean to you. Yeah, so you listened to me yesterday. It totally depends how you connect the battery. So right now, this was a trick question. If you go up to the power supply, you don't know which one's positive. You don't know which one's negative. So I just asked you a question you can't answer. Okay? It doesn't matter which way I attach the power supply. Which side would you like me to be which side you want positive? The left side. Okay, now we're going to set all of our chemistry. Negative, sorry, positive, negative. Now we can answer. The positive terminal is which electrode now? It's the opposite of voltaic. The positive is now our anode. Okay? So it's so opposite of voltaic cells, it would have been negative, but in electrolytic, it's positive. When you get an electrolytic question, I want your eye to go right to that battery. As soon as it goes to the battery, label anode and cathode, and then look to see what chemicals you have. Okay? None of the stuff we did up above matters for anode and cathode. Okay? Now everything that's going to happen comes from just understanding the chemistry and all the skills we've been working on. Let's see, our cathode is going to make a neutral metal. There's our cathode, our negative terminal. So zinc is going to go to that cathode and coat it. Okay, the cathode's going to get heavier as it gets coated in zinc. And cations are going to go to the cathode. Anions are going to go to the anode. And the lead is going to combine with that anion and make an ionic lead sulfate. And you'll see little chunks forming below the electrode. As this electrode loses mass, because this lead is a reactant. So you're going to see this electrode get lighter, this electrode get heavier. If you flip the power supply, you'd flip everything. So that's pretty much everything you need to know about electrolytic cells, but you're going to have some work time to practice drawing them, understanding, knowing which one might get lighter, which one might get heavier. Sometimes neither electrode changes mass. Okay? There are lots of half reactions that don't have any solids involved. So if you had this fluorine fluoride isn't going to affect the mass of any electrode if that happens. Okay? But a lot of these half reactions have metals being made or a metal reacting away. So I have a fair bit of practice to start with. On page 640, I'd like you to take a look at number 2, but in particular number 5 and 6. And 5 and 6, I just have a picture right up on the board. So if students ask me, if you don't have your book, you can look right here. When you finish those questions, so 640, 5 and 6, then I'm going to flip and I've got some more practice for you to do. Okay? And we're going to practice for at least the next 45 minutes or so. Okay? Okay. The next lesson are some anomalies, some quirks to electrolytic cells.